In this DSM demo video, I will go through the output of more advanced dynamic multi-level models, in which we bring in the structural equation modeling component at the between level and do more exciting stuff at the between level. So this is a follow-up on the part 1, in which we were just allowing the random effects at the between level to be correlated with each other. And it's also associated with two videos about the input of these kind of models. So if you haven't seen those, you might want to check out these videos first. So where we left off in the previous part is with this model, in which we said we have a dynamic model at the within level, and all the parameters there are allowed to be random. So they are allowed to take on different values for different individuals. And this is indicated with the filled circles here for the regression coefficients and also for the residual variances. Now these filled circles correspond to open circles at the between level. And what we see is that, for instance, this autoregressive parameter here for closeness is now a random variable here. So, and it's allowed to covary with the other random effects that we have at the between level. So we in total have 8 random effects. 2 are the individual means that come from the decomposition. We have 4 slopes, the 2 betas and the 2 phis. And then we have the logs of the residual variances also. Now, instead of allowing all of the random effects to be correlated, as we have done in this model, we can also do some structural equation modeling here. And the first model we're going to consider is a model in which we allow the relationships between the random effects to be accounted for by one latent variable, which we refer to as the common trait, or CT. So what I'm going to say is the common trait is measured by the 2 components from and between person components from the decomposition, so CL and TE, and then phi CL up to log VTE. So that's in the code here, phi CL up to log VTE. So all of the random effects that we specified at the within person level actually become now indicators for this latent variable at the between person level. If we use a by statement in Mplus to specify a latent variable, then the default is that the vector loading of the first indicator will be fixed to 1. So that's this one here for CL. So that's fixed to 1 for scaling. All the other vector loadings will be freely estimated. However, if I specify this model, what happens is we are going to get an error. And the error implies that we have to give a starting value for the following statement, CT by phi CL. So it's talking about this one here, the vector loading for this one. So that's this arrow over here in our path diagram. We have to specify a starting value for this. And one way that we can do this is just indicating, we just want to specify a small value for this value close to 0. So with the asterisk, that's to indicate this is just a starting value. So it's not fixed to this value, it's only a starting value. And then I indicate beta CL up to log VTE. So that's the second one here up to the end. So I still have the same indicators in my model. And if I do it like this, then the model will just run fine. These are the parameter estimates that we get. So the first one, the first vector loading, you see the by statements. The first one is actually fixed to 1, so it's not freely estimated. It's not so interesting. The other ones are all freely estimated. And we see that some of them have credibility intervals that do not include 0. So for those parameters, we have evidence that they actually are different from 0. And there are also some credibility intervals that actually do contain 0. So for these parameters, we would say there's not really evidence that these are different from 0. When we look at the path diagram, we can include the parameter values like this. So I indicated the parameters for whom there's not really evidence that the parameter is different from 0. I made those arrows light gray. The positive ones I made red. And the negative ones I made blue. So this one was used for scaling. It's fixed to 1. So it's a positive relationship. The second one, we see it's a negative parameter, minus 0.660. So that's this one here. Attention regressed on or loading on the latent variable CT. We can also include those numbers in our regression equation. So this is the first one for closeness. The factor loading is fixed to 1 for scaling, so that one is not estimated. But we can also include the ones that are, for which we found evidence that they are different from 0. So for instance, the phi parameter here, it also has a negative factor loading. It's this one over here. And if we look in the code, or in the output, I should say, and this is actually the value that was estimated. So that's the number that we can fill in here for the arrow, and also then here for the regression coefficient. And we can do this for all the different ones that we find and that are different from 0. We also get intercepts. The intercepts are not included in the path diagram, but we can include them, or you can see them where they are actually in the regression equations. These are the intercepts, the gammas here. So this one is the one for closeness. It's the first one. And then you can fill in the other numbers as well. There's one for which there's no evidence really that it's different from 0. So that's why I made it gray here. We also get variances and residual variances. So what we get is the variance of the common trait. So that's this one. And then we get the residual variances. So these are the variances of the parts that are not accounted for by the common trait. For each of these, you see that the credibility interval does not contain 0, but that's not so interesting because by default, these credibility intervals will not contain 0 for variances, so that's not so informative. When we move to a next model, we are going to include an observed variable at the between level as a predictor for the random effects, and in this case, this is the variable neuroticism. So we have to indicate in the use variables command that we have another variable that we want to include. We indicate also that it's a between level variable only, so it only contains variability across individuals but not within a person. So within a person it's a constant. And we also indicate that we want to use ground mean centering for this. I will explain in a couple of slides what the difference is if we don't do this. I will show this. And what we are going to say is at the between level, we want to regress all 8 random effects that we have in our model. So the 2 means, the 4 slopes or regression coefficients, and the log residual variances. All of these are going to be regressed on neuroticism. And what we see in the path diagram is, and neuroticism is an observed variable, so that's why we indicate it with a square. And it has arrows going to all 8 random effects in our model. The 2-headed arrow here is the width statement that you're going to get by default. It's the residuals of these components that are going to be allowed to be correlated. If you don't want this, you have to fix it to 0, as I explained in the video on the input for these models. So we're not going to focus on it here. If we do this, we get the following parameter estimates. We have the on statements, the 8 on statements, and these are the parameter estimates that we get. So again, we can look at the credibility intervals and see which ones contain 0 and which ones do not. So we see these 3 actually overlap with 0. So that means that for these parameters, there's not really evidence that they are different from 0. Whereas for the other ones, we find credibility intervals that do not contain 0. And therefore, we can say there is evidence that these parameters differ from 0. When we look at this in terms of the path diagram, we can actually fill in the parameter estimates like this. So we have, for instance, the phi of closeness, so the autoregressive parameter of closeness, regressed on neuroticism. We see it is this value 0.013, and that would be this arrow in the path diagram. I indicated it in red to indicate it's positive. So if a person is higher on neuroticism, they tend to have a higher autoregressive parameter for closeness. And similarly, we can fill in the other values for which we found evidence that they differ from 0. So we see also that if a person is higher on neuroticism, they tend to have a lower mean on closeness, a higher mean on tension, a higher autoregressive parameter for phi. And then this one is the most tricky one actually. So higher neuroticism score is associated with a lower parameter beta CL, so that is the effect of tension on closeness. And how to exactly interpret this, I will have to explain in a different video. For this, it's very useful to make use of the plotting options to actually see what this relationship looks like. We can also fill in these regression coefficients, of course, in the regression equations, and this is what you see. I just filled in the numbers. So for instance, this one for phi CL, we see it over here. And then the one for beta CL, we see it over here, and so on. And notice here that I'm using the centered version, the grand mean centered version of neuroticism. So every person has their own score on neuroticism, but we subtract the grand mean or the sample mean from this. So it's only deviation scores, and the average of this predictor therefore is equal to 0. The intercepts we get are over here. Again, we can look at which ones have a credibility interval that contains 0 and which ones do not contain 0. And while we do not see these intercepts in the path diagram, we can actually include them easily in our regression equation. So here we have the intercepts. So for instance, the intercept for CL, we see it over here. It's this intercept here. And then we have the one, for instance, for the autoregressive parameter of CL, this number over here. And we can fill it in as the intercept for phi CL, and so on. So the difference between grand mean centering and non-centering is over here. So here we are looking at the results when we are using grand mean centering for N, for neuroticism. And here we have the results if we don't use this grand mean centering. If you use the exclamation mark, then Mplus is not reading this code. So this is just comments that you can include for yourself. And what we see is that the numbers that we get for the intercepts are really quite different. And to understand this, it's helpful to actually look at what the difference between the regression equations is when we are specifying it, either with the grand mean centered or the non-centered predictor. So if we are using grand mean centering and we are focusing on the phi parameter, so this is the intercept here. We have the regression coefficient from a previous slide. And what this means is that, well, if we are looking at what do we expect the autoregressive parameter for closeness to be for an individual who scores average on neuroticism. Well, if a person scores average on neuroticism, their score here is actually this n bar, so the average. So this will then become 0, which implies that this whole term here basically cancels out or drops out. And what we are left with is that we expect the person to have this as their autoregressive parameter for closeness. If we, on the other hand, look here, what we have is, well, we have again the intercept for the phi CL parameter. That's this parameter over here that was estimated. And now, if we say, okay, we are looking at a person who scores average on neuroticism, yeah, it's just filling in n bar here. And so we should know what n bar is to be able to figure out what their expected value on phi is. It also means that what this intercept here means is, well, it's the value we expect for phi if the predictor has a value of 0. And in this case, it depends really on what kind of scale you're using, but a score of 0 might not even be possible on this predictor. In this case, this is actually true. It's not possible to have a score of 0 on this variable, and so this intercept is really not very informative. If we look at the distribution of the neuroticism score in this sample, this is what it looks like. So it has a mean very close to 50, and what you see is if you fill in 50 here, basically you will get a prediction here that is very similar to this intercept here. So the point of this is that, at least in my opinion, when you are including observed predictors for the random effects, it's very advisable to use ground mean centering for these predictors. But yeah, I don't know, maybe other people disagree, and maybe there are cases where it's really useful not to ground mean center. But yeah, be aware if you're trying to interpret the intercepts that ground mean centering or non-centering really makes a huge difference in what the intercept represents. We also get this with statement in our output. We didn't ask for it explicitly, but by default, the components from the within decomposition, so that's the between person components, will have residuals that are allowed to be correlated when we include observed predictors for them. And this is, in this case, the covariance. So mind you, it's not a correlation, so we cannot say that this is a strong or a weak relationship. All we can say is that it's a negative relationship. We already have a negative relationship modeled between these two variables through this relationship here. So this is negative because one regression coefficient is positive. Sorry, this one is positive and this one is negative. So this already accounts for a negative relationship between these two, but this is then further adding to this negative relationship between the average on closeness and the average on tension. We move to the final model, in which we include not only a predictor for the random effects, but also an outcome variable, in this case relationship satisfaction, which is also an observed variable. So we add this to the use variables command, and also at the between, we indicate it's a between level variable, so it only varies across individuals, not within individuals. I'm not using ground mean centering for it. I could, but it's less of an issue for outcome variables. It's really the predictors for which it's important to use ground mean centering. And what we are going to add here at the between level of the model is that we want the relationship satisfaction variable to be regressed on the 8 random effects and then also on neuroticism. So that would be this direct effect, and then we have these mediated effects through all the different random effects. If we look at the output, this is what we get for the parameter estimates. So we have the on statements where all the random effects are regressed on neuroticism. And again, for some we have evidence that they differ from 0, for others we don't. We can also look at whether they're positive or negative, of course. When we then move to the equations, we can actually add or include those values in the equations. And when we then move to the second part, where relationship satisfaction is regressed on the random effects and the 2 components from the decomposition and the observed predictor neuroticism, and we see that only one of these actually shows evidence that it's different from 0, and it's the one for the average of tension. So higher on average tension implies lower relationship satisfaction. If we then include this, when we think about this in terms of the regression equations underlying this model, this is what we get. So we see that quite some of these random effects can be predicted from neuroticism, but relationship satisfaction only depends on the tension mean. And then there's of course an individual residual also here. If we look at this in terms of a path diagram, we represented it in a bit of a different way now. So what we see is we have the observed variable neuroticism. It has a negative effect here on these two random effects, but positive effects on some others. And then when we go to relationship satisfaction, we see that there's only one for which we have evidence that it differs from 0, and it's this one, it's negative. So in this case, we could say, well, we have found some evidence for a mediated effect of neuroticism to relationship satisfaction, and it's mediated through the average of tension in the relationship. So high neuroticism is associated with a higher mean on tension, which in turn is associated with a lower relationship satisfaction. And that's it for this video on the more interesting models for the between person level.